Okay, well, good afternoon again. I'm here today to talk about my PhD dissertation, which is a probabilistic ontology, representation, and modeling methodology. And everybody knows here, but my advisor is Dr. Laskey. Okay, so just start by giving you the agenda. I'll start with a brief introduction, where I'll talk about the problem statements and then describe what are the problems and then talk about the contributions on my dissertation. Then we'll go and talk a little bit about representing uncertainty in semantic technologies. And then I'll talk about my first major contribution, which is the extension of the Probabilistic Web Ontology Language. And we're going to talk more what that means later. And the second major contribution, which is the uncertainty modeling process for semantic technologies, a methodology I'm proposing also in this dissertation. And then talk about some conclusions. Okay, so introduction, a summary of the problems here. And I just want you to keep this in mind as we go through, but I'm going to talk in more detail why this is important as we go through the presentation. So the first major problem is the lack of mapping and types in Prowl. So the Probabilistic Web Ontology Language, Prowl, does not have a well-defined integration between the deterministic and probabilistic parts of the ontology. So that's a problem. The second problem is the lack of methodology. So all these different probabilistic languages that we have for semantic technologies like Prowl, they lack a methodology for guiding you how to create these models, how to create these probabilistic ontologies. But again, it's going to make sense as we go through all this stuff. I just want to keep this in mind. So for the first problem, what I did is I extended the Probabilistic Web Ontology Language, Prowl, in order to allow this integration between the deterministic and probabilistic part. And in order to test that, I led the development of a proof of concept tool, which we developed in collaboration with the University of Brasília. And for the second problem, which is the lack of methodology, I developed a methodology for modeling the probabilistic ontologies. And then I used the methodology in two different use cases to show that it works. Okay? So now, well, what's the problem? What's the motivation for all this, probabilistic ontologies and this methodology and all that? Okay, so I'm going to talk about here an example I'm going to use throughout the presentation, which is finding frauds in procurements in Brazil. And I'm going to describe a little bit of how a system would work on that domain. So we have a lot of, piles and piles of physical information, these documents all over Brazil, of the procurements that happen, public notices and things like that. So when the agency I work at in Brazil, General Controller office. When people have to do auditing inspection, they go to these specific cities and different states, and they have to go through all this physical documentation to gather information they need in order to evaluate if everything's according to what it was supposed to be, if you have some fraudulent activity or something like that. So once they gather all that information, then they have to fill and put all that information into our system, into a database where that information is going to be available. Well, here, this, is what happens in our system, but this is actually what happens in a lot of different systems also. You do some activities and then you put your database into your system. The problem actually here is that, just to give an example, in just one of our databases, which is the transparency portal, we have a lot of information there. We have more than 1 billion different informations available on that database, involving more than $5 trillion US dollars. So you can imagine it's a lot of information. And one problem that everybody, all the experts complain is that, I waste a lot of time putting all this information in this database. But what do I get in return? Some things are obvious, like, you can search faster for information, then you can look for what people did on different reports in the past and so on. But they really want something that helps them identify if there is some fraud occurring there. So they want to use that information available here, and the tool tell them something useful. So what's happening really is that we're shifting from this scenario where we have a lot of overload of physical information to an overload of digital information. So it's still here when the expert needs to go through all this different information. They have to connect the dots, which is really hard because it's a lot of information there. And you can imagine we just have 3,000 people working roughly in our office, in our agency. And you have we're talking about millions of projects, thousands of projects, and money here. And it's really tough for them to go through everything. It's not possible to do that, okay? So, how do we solve this overload problem? So one idea is to have this automated reasoning system that, we are able to model the expert knowledge into this, into this design, into this model, and then use that to say, okay, when you have this kind of information, then it seems like this procurement is okay. But if you have this other kind of information, then this procurement is suspicious because it seems like something wrong is happening here. So you're gonna, represent the expert knowledge in this model. Once you do that, then the tool uses that information and uses the information available from the database and the knowledge represented in this domain to do some inference with it. And doing that inference, then you can get some information that tells you, for instance, the likelihood of having some suspicious activities there, for having some suspicious procurement. Okay, with that, we can then apply some filtering rules that says, okay, if the probability of having fraud here on this procurement is greater than 30%, 50%, whatever you decide is your threshold, then you're going to automatically create this report and send to the respective department of your agency, which is gonna, this person is then gonna look into this information and see if okay, now we have, we went from data-driven information where you have to look all this different information to just a few scenarios where we have more knowledge about what's happening. So, this is gonna help the experts. So it's not to say that if the tool tells you that you have a fraud, and high probability that you have a fraud, it does not mean that you have a fraud in that procurement. It just means that you should take a better look at it and see if it's really a problem or not, which is better than just picking at random different procurements and auditing them. Okay, so that's the idea. And what I'm trying to show here, and I'm going to show examples of that, is that we can use probabilistic ontologies in order to to design the expert knowledge into probabilistic ontologies and use that for inference. But before we talk about that, I have to talk about what's semantic web and what's an ontology. So the semantic web is actually a web of data that can be processed by machines. And one example of being processed by machines is that, for instance, if you think about 3 pounds, depending on the context where it's being used, it can mean the price of something or the weight of a product, right? So, we want to allow machines to differentiate between the two when this string of characters is being used to define, price, when the string of characters is being used to define weight. So the semantic web is going to allow that differentiation for machines. So we're changing the focus from just looking at data and actually having some knowledge associated to that data. And the machines can have that and use that information. Okay, so the World Wide Web Consortium, it states that ontologies provide the cement for building the semantic web. Well, ontology is actually a word taken from philosophy where it means the systematic explanation of being. But what does it mean in our context? So in our context, an ontology is a formal representation of some domain of application. Well, what does that mean? Well, we're going to define types of entities, which we also call classes. So we're going to have person, procurement, enterprise, and some other classes and types of things we're going to have in our domain. And these classes, these types, are going to have attributes and properties associated to them. So you have a person has a first and a last name. A person, procurement has a procurement number associated to it. You have a relationship between those classes. You know that a person is mother of another person. You know that a person is owner of some enterprise, and so on. We also are able to represent processes and events where we have, analyzing if requirements are met, choosing the best proposal. So those are all things you're going to represent about your domain of application. Okay, well, one language that is used a lot by the community is called Web Ontology Language, OWL. It was actually developed by the W3C. And it is a language to represent ontologies for the semantic web. And it was proposed as a recommendation. It was accepted as a recommendation back in 2004. And actually have a second version now, OWL2. It was proposed. It was accepted as a recommendation from 2010, last year. So how do you represent that ontology? So you can see here in a tool called Protégé that it's the standard tool for developing OWL ontologies, and the community uses a lot. And you can see here on this side that we have the things that I was talking about. You have person, you have enterprise, procurements, and so on. And you have down here attributes associated to that, to those classes. So you have, for instance, is front for, so the person is a front for some organization. And on the other side, you have the definition of these classes. For instance, frontman is defined as a person, is the equivalent to a person who is a front for some organization. So you have a crisp definition for that concept, frontman. However, we have two problems here. One is that not every class is going to have a crispy definition like this one. Okay? So for instance, we talk about the rich person, or a poor person, or maybe a famous person. How do you define a famous person? Is it going to be a person that has more than 1,000 followers on Twitter, or 1,005, or 5,000? How do you define that? It's not clear, right? So you need uncertainty to define those kind of concepts. Also, it's fine here you have a crisp definition saying the person is front for some organization. However, this information about the person being a front for some organization is actually usually not known. It's usually what you want to understand. It's what you want to have some likelihood and say it's likely this person is a front. So it's also useful to have uncertainty here, and that's where it plays a key role. And the other thing I want to mention is that once you have the information available about those concepts, so once you know John is a person and John is a front for some organization, then you can apply some inference rules that is going to classify this person now as a front man based on this rule. So those are things you can do with ontology. Okay, so I talked about the things places where we want to apply uncertainty to, and this is actually known by the community. The community recognized the need to represent and reason with uncertainty, and that's why the W3C created back in 2007 an incubator group, which was responsible for studying the different ways to represent uncertainty on the semantic web. Well, one of the things they concluded on their final report was that really, we need a standardized representation for uncertainty on the semantic web. And that's needed, but no language out there is mature enough to be used as a standard. The only thing I want to say here is that Probabilistic Web Ontology Language, Prowl, is a candidate language to represent probabilistic ontologies. And this language, Prowl, is based on Multi-Entity Bayesian Network, MEBN logic. And I'm going to talk more about that. Okay, so I described what an ontology is. What is a probabilistic ontology? So basically, a probabilistic ontology is everything we talked about before. So you have the types, you have the properties, you have the relationships, you have the processes and events, but now we want to talk about uncertainty about all those different kinds of concepts you already have. So, yep. Fabio?
Hi, Rommel. Which view graph are you in?
Sorry, I'm on 11.
Okay, fine. And that's it.
So I'm,
When you change the slide.
Yeah, I have to. Yeah. So I want to talk about uncertainty of all these, terms I define on my ontology. For instance, I want to be able to say that the probability that a person is a front for the enterprise, given some other information, is 90%. Okay, so that's the kind of thing that I want to represent on probabilistic ontology. So next slide. Here you have a standard tool, like you have Protégé for a standard tool for modeling all ontologies. We have UMP-Bayes as a standard tool for modeling probabilistic ontologies in Prowl. And here I'm going to talk about what all these things mean later on. But here I just want you to understand the idea behind this. These are random variables and relationship between them. So this is similar to a Bayesian network. And I just want to give you an idea here what we're trying to say, which is similar to the expression I just gave you on the previous slide. Here I want to say that if the person has a person is more likely to be a front for the enterprise, if the enterprise who he's responsible for, won millions of dollars in procurements, but this person just makes $5,000 a year, well, that's kind of strange. The enterprise he owns makes lots of money, but he's not making any money, so that's suspicious. So you would like to classify that person, as more likely to be a front for that enterprise. The same thing goes with education level. In general, you would think that a person that owns or is responsible for an enterprise that makes, millions of dollars, this person should have at least high school or some education. If this person has no education at all, or just middle school, then you would think it's more suspicious that this person is a front for that enterprise. Okay, so again, just the concept I want you to have here, and I'm going to explain later what all those different kinds of nodes are. So now I'm going to talk on slide 13 about the first problem, mapping, which is the lack of mapping and lack of types. What I want to do here is you can see just a snapshot of the ontology we had before. We have front man. And on the other side here, we have the probabilistic ontology definition. We have this rule, when is more likely this person is the front for this enterprise. What I really would like to do is to use the information I have available about this ontology. So I now have an instance of a person, which is John Doe. And John Doe has an education level, middle school. I know his annual income is $5,000. I want to use that information to instantiate these random variables and now be able to do probabilistic reasoning and say, okay, given the information available on my ontology, I know that John Doe has a probability of 90% of being a front for IT business. So that's the kind of thing I want to do. However, in order to do that, I need to be able to, I have to link somehow the is front for property on my ontology to this random variable here on my probabilistic ontology. I need to do the same thing for all the other nodes. So has education level has to be linked to that random variable, has annual income to that other random variable. However, the problem is that in Prowl 1 today, we don't have a way to represent that link. There is no way to represent, which properties are related to which random variables. So we really, if you want to instantiate those random variables, we don't know which value goes with what random variable because they are not linked and the machine cannot just guess, right? We need to represent that on the language. The other thing I would like to be able to do is to say that these random variables here, like has annual income, has as a possible value a data type float, like I do on my ontology. So in my ontology, I say has annual income, some float. So the range of that property is a float. However, in Prowl 1, it's not possible to reuse data type available, which is already defined on my OWL ontology. If I want to do that, first I have to define in Prowl 1 what a float is, and then I can use that float as a possible type. But that doesn't make too much sense, because if I already have defined on a language that I'm using, why not just reuse it instead of having to redefine everything, right? So I want to be able to do that. Okay, so remember we talked about here, the scenario where we're trying to have a system trying to identify frauds and public procurements. And now my question is how to build probabilistic ontologies, slide 14. The big question is that these models that I have to represent all the knowledge from different experts is really complex. If you think about it, in the example we were talking about, if there are some types of frauds, they're general for any scenario, for any case. But some of them are just specific to IT business or to things associated to road constructions. And we want to gather information from all these experts and put it inside one coherent and consistent model. So that's something really hard to do. It's really complex. Not only that, but we also have, remember I was talking about using probabilistic ontology as a way to represent this, these models. And these probabilistic ontologies, they put together logic and uncertainty. Those two things separate by their own, they are already challenging enough and really complex to build models. If you put those two things together, it becomes even more complex. So it's really a hard thing to do. And that's why I've actually received a lot of questions from different people asking, how do you come up with these models? So it seems useful. I want to use it. I think it's really what I need right now, but I don't know where to start. So that's why I got different emails, and I'm just going to show a few here. People asking, it's been a little hard to understand how to put in practice a probabilistic ontology. So it's like, I understand, I want to use it. How do I do it? Some other people asking, how do you identify which entities are relevant to the problem and how to translate them as variables in your system? So you can see they're all asking about the same thing. How do you do it? And the other people, another person saying, okay, I'd like to explore if and how it can be used for applications on my area for resource, using resource devices. Another one says, okay, why use these variables? Why they're connected such a way? How do you choose what type of variable I should use in here? And finally, last one I want to show you is a person that said a lot of things, but then he talks about how one reach from a problem description to a MEBN at times is not clear. And MEBN is just a specific language that is able to represent this probabilistic ontologies, which is behind Prowl. And then he goes and he asks down below here, should we follow an object-oriented approach when identifying important entities, or should we think in terms of predicate logic? As a modeler, what drives our thinking process? So, this is really what drove me to think, okay, I think I'm going to do this in my dissertation. At first, I just thought about doing the extension of Prowl and doing that link between the deterministic and probabilistic part of the ontologies. But I myself asked a lot of these questions when I had to create the models using probabilistic ontology and using Prowl. And then, I realized, okay, there is a lot being said on the literature about what Prowl is, how to implement it, where it can be used. And there is even emerging literature on ontology engineering. But really, little has been said about how to model probabilistic ontologies. And this is not only associated to Prowl, it's actually associated to other languages that allow the representation of probabilistic ontologies, like Bayes-Al, OntoBayes, PRMs, Markov logic networks. They all lack this methodology on how do I come up with a model from the problem description. So now in slide 16, the contribution, where I talk about the contribution. So for the first problem, where I have the lack of types and the mapping between the probabilistic and deterministic part of my ontology, I extended the Probabilistic Web Ontology Language, Prowl, in order to provide this mapping between the deterministic and probabilistic part of the ontology, and to allow the reuse of existing types provided by OWL. And to try those ideas, I led the development of a proof of concept tool in collaboration with the University of Brasília. For the second problem, which is the lack of methodology, I developed methodology for modeling probabilistic ontologies. And I created 2 use cases using the proposed methodology to show that this methodology actually works. So now in slide 17, representing uncertainty semantic technologies. I'm going to talk a little bit about this. So in a deterministic semantic web where we just have ontologies, we'll either consider something to be true, to be false, or to be unknown. So a really shortcoming is that there is no built-in support for uncertainty. In an open world environment, approximate or partial information is more the rule than the exception. And I gave you some of the examples before, is front for how to define, definitions that are not crispy. But I'm going to give you another example here. So imagine I have this ontology, and this ontology has these rules. If 2 people have the same mother, then they're siblings. If they're siblings, they're related. And then I have this more complex rule that says, if a person is a member of a committee for a given procurement, and he's related to a person who is responsible for an enterprise bidding on that procurement, then I have a violation of law. What's behind this is basically if my brother is bidding a procurement that I'm responsible for, I might end up saying things that I should not on a Sunday barbecue, or even tell him some stuff, some privileged information, just because I want him to win the procurement because, I know my brother is in a bad situation, he needs some money, so I'm just going to help him out. But I can't do that, right? Because it has to be a fair competition. So that's why this is not allowed. So imagine now I have this information here that says John is a member, of the committee for procurement 34. I have that IT business is participating on that procurement. And I have to go back. Sorry about that. And I have that Richard is responsible for IT business. So now imagine that I also have the information that John and Richard, they have the same mother. Well, if they have the same mother, then I can infer they're siblings. I can infer they're related. And given this other information here, I know he's a participant, he's responsible for that enterprise, and they're related, so I have a violation of law. So that can be inferred by this information available. But imagine now that I don't have this information. I only have the information that John and Richard, they live at the same address, and they have the same last name. Well, can you say for sure they're related? And not really. I mean, at least in Brazil, a lot of people go from small cities to live in big cities, but they live on the place where they're going to work. So we have maids and gardeners actually living on the place they work. So, the fact they live on the same address does not mean they're related. And also, White must just be a common name. So it's just a coincidence they have the same last name. But still, it would like to say that when you have this kind of information, it seems to be more likely they're related. Therefore, it's more likely you're going to have a violation of law. Okay, so that's the kind of thing that uncertainty allows you to do, which just ontologies do not, because you would just ignore this information and say, okay, I do not know if it's a violation of law or not, even though it seems like it is. So we want to use that information. Just ignoring is not enough. And again, I showed this slide before, it's slide 19. The community recognized the need to represent uncertainty. That's why they created an incubator group, which says, one of the things they concluded on the final report was, we need some standard representation for this. And I just want to point again, Prowl is candidate for representing probabilistic ontologies, and it's based on MEBN logic. So let's talk a little bit about what MEBN logic is and what Prowl is. So here on the top, you have this set of random variables here, which we call MEBN fragment. So this is a fragment from the whole model we have, okay? And here we have 3 different types of nodes. The first one I'm going to talk about is the isFront4, the one here on yellow down below. This is called a resident node. And it's a resident node because it has its probability distribution defined within this mfrag, okay? These other nodes here in gray, they actually influence the distribution for this node, but they have their probability distribution defined somewhere else in another mfrag. And the final thing you need is the constraints. When are these relations true? When can you use this relation? Well, only when these context nodes are true. In other words, if I'm talking about a person being a front for some enterprise, that only makes sense when I'm talking about a person who is responsible for that enterprise. It's not just any person. It has to be a person related to that enterprise somehow. So that's why here I say that this thing has to be true. This person has to be responsible for this enterprise. Also, the same thing happens with procurement. If I'm talking about a value of a procurement, it better be the value of a procurement that was won by the enterprise I'm talking about. Otherwise, it doesn't make sense. So that's why I have another context node here that says, okay, the enterprise has to be the winner of that procurement, and so on. So that's the 3 different types of nodes we have. And you can see here that this node, this front4, is defined local probability distribution here. So it's resident node in this mfrag. But in this other mfrag, it's used as an input node. Okay, so the probability distribution is in here, not in here. But it influences the distribution for this other guy. This exists fronts in enterprise is pretty much saying that if I have at least one responsible person who is a front for that enterprise, then there is a front on that enterprise. It has to be just one. This is actually a built-in operator in MEBN, existential operator. And here I just implemented in a separate mfrag because of a limitation in our tool, UMP-Base. But this is actually built into the MEBN logic. And then we can use this here to say that if there is some enterprise with a front, then we can say that it's more likely to have competition being compromised. Because we want to have different people that actually have command of the enterprise, that they're actually able to win their enterprise and not somebody else commanded the enterprise for them. So that's the things you're going to have on your MEBN model. And then you put all these different mfrags together, and that's what we call the MEBN theory. And this MEBN theory is going to be the domain, the model you just described for, in this case, fraud detection. Okay? So what's happening is that once you instantiate all these variables to talk about your specific situation, the question you're trying to answer, this MEBN logic is going to guarantee you're going to have just a unique joint probability distribution. So that's something that we're going to be guaranteed by the logic. But why use MEBN? Why not just use BaseNet, and you can maybe separate them in different fragments? Why not just do that? This seems to be really complicated. Well, one really important thing that MEBN allows you to do is to represent repetitions. So, for instance, if you just in your specific scenario, you're just talking about one enterprise participating in that procurement, then you create these nodes just once, and then you fill out the values for that specific enterprise. So, talking about enterprise 3 and person 3. However, if you have 2 different enterprises, now you can see that we have another set of nodes here, which are basically the same as this one, but they have different values because they're associated to a different enterprise and to different people. And so on. All these different Bayesian networks have 3 and 4 enterprise participating in that procurement. You're going to have more instantiations and different networks which are going to be used to answer your specific question. Okay, so what about Prowl? What is Prowl? Well, Prowl is a language that allows you to represent your MEBN model as an ontology. So you can actually see that all the things we've been talking about here is that you have a node, a context node, input node, resident node, mfrag, m-theory. Those are things you have represented in this upper ontology we call Prowl, which allows you to define your probabilistic ontology in using MEBN logic vocabulary. Okay, and again, UMP-Base is going to be a tool that it's going to make your life easier. So you don't have to worry about all those names and attributes that you have on the probabilistic ontology defined there. You just drag nodes around and you drag an arrow from one node to the other, and that's behind the scenes what's happening is that all these instances are being created and they're being related to each other. Okay, so let's finally talk about my first major contribution, which was the extension of Probabilistic Ontology language. So just to refresh your memories, remember the problem is that we need an explicit link between properties on my ontology and random variables on my probabilistic ontology in order to be able to instantiate this specific Bayesian network to do my probabilistic inference. And I also would like to use data types on random variables here. So here my goal is to talk about how you represent a random variable today in Prowl 1. Okay, and then I'm going to show what's the problem, why we need the explicit link. Then I finally explain what I did when I extended to Prowl 2. Okay, so that's the idea behind this. This is going to be kind of a long slide. So now we can have a property here, which is actually a function, which has the domain being a person. So it can be represented here as this node right here. So it has the domain person and the range education level. So we're talking about the person has education level. Slide 26, Fabio. So now I want to talk about, this was my ontology. Now in my probabilistic ontology, I use a thing called a random variable called has education level. And today it's represented as, has education level random variable. This random variable has one argument, which is person. This person is the first argument of that random variable. And it's associated to a local variable, which we call ordinary variable, within the xamfrag, which is called person, and the type of that variable is person, the class person from my ontology. And you can see here that it's defined that the possible values for my random variable is actually the education level, which is also, it's consistent with this definition of the property here in my ontology. So what's the problem? Well, imagine now that, besides having this property has education level, I have another property that is aspires education level. This aspires education level has the same domain, so a person aspires, a certain education level. So now imagine I have a, John, he has just middle school as education level, but he aspires a PhD, right? So my question is, when you're trying to instantiate this random variable, how would you know if you should use middle school or PhD? Well, a human being know that for sure. Has education random variable, I'm actually talking about the has education level property. But a machine would not know that. It needs to be explicit. There is nothing that tells me that I should use middle school and not PhD, right? So that's why I need to have an explicit link on my language, and that's what I did in Prowl 2. Say that this random variable is actually defining the uncertainty for this specific property. Okay, now I know that I need to use my middle school. Oh, that's not all, because in MEBN and in Prowl, you can have n-ary random variables. So I could have another argument. For instance, if I want to talk about not just the degree that I got, but also, who was the divisor when that person got that degree. So we have this other argument here, who is the divisor. And just for sake of example, let's say that, Rommel has a PhD degree, right? And his advisor is Dr. Laskey. Okay, so let's look into this detail here. So now I have another local variable like this person, but it's going to be advisor. And this different variable, it's going to be related to another person, okay? And this person now is associated to actually a different property. It's a property called has education level advisor, which tells who is the divisor for that person. So if I just have this information, then I have the same problem I had before with the random variable. Well, who is the person and who is the advisor? So if I don't tell my machine explicitly which property I should use to fill the value for these variables, the machine might end up saying that Dr. Laskey is the student and Rommel is the advisor. And we don't want to do that, right? So basically here, what we need is to create the explicit link saying, okay, this person variable argument is actually the domain of this property has education level. So a person, so Rommel has education level PhD. So Rommel is the domain, which is the person I'm talking about in my random variable. And that's why I have this different thing called is subject in, which means the domain. But for the divisor, is the other way around. It's actually the range, because I'm talking about Rommel has education level advisor, Dr. Laskey. So now I want to be the range of that property to be what fills the value of this argument. Okay, so basically that's the main idea behind what was done to link this stuff. There is a lot more to it. You can see that in the dissertation. But to clean it up, if you want to define now in Prowl 2 a random variable like this one, you have to say that this random variable defines the uncertainty of certain property. And for every argument you have to link to the domain or range of a property in your ontology. Okay, so that's how mapping schema was done, and now we're talking about existing types we're using existing types in Prowl. So this is actually classes and things that we have in Prowl 1, and I just want to focus here in one definition, which is nodes on slide 17. Nodes can have as possible states entities, and these entities can be Boolean random variable states, categorical nodes, object entity, and so on. I'm just going to show you how you can replace these classes and subclasses by things that already exist in OWL. So for instance, Boolean random variable states can be replaced by Boolean data type from our OWL ontology. Okay, categorical random variable states, which are low, medium, and high, we can replace by nominal classes, which define which are the individuals that represent that class. For instance, individual low, medium, and high. For object entities, pretty much we're talking about classes, right? So we can replace by the OWL ontology class. And this meta entity we're not going to need anymore because this entity is actually something just needed to represent the structure. We're not going to have that anymore, so there's no need to have it. And the other thing I want to be able to do is not just represent Booleans and categorical values and classes. I want to actually talk about data types to talk about, floats and integers and dates as possible values for my random variables. So I added that. So finally what I did is you can see that Boolean is actually a subclass of data type. So I just defined that a node has as possible values either a data type or a class, which covers the other two, nominal and class. Okay, so that's basically how to solve the problem of using existing types. And to test these ideas out, we developed a proof of concept tool, which now you can see here. You've seen this picture before, but by itself. Now you can see that you have the protege tool inside UMP-Bayes as a plugin. So you can see your ontology, you can edit, you can create your classes, your properties, all inside UMP-Bayes using protege, and you can even load ontologies that you had done before using protege. Once you do that, you can go to this other tab here and say, okay, now I want to talk about the uncertainty for this ontology. And what I do is I look at the property I want to talk about here, and I want to say, okay, this is related. I want to create a random variable here. So I drag and drop on my mfrag, and it's going to create this random variable for me. It's going to map automatically to that OWL property from my ontology. And it's just able to do that now because I do have that language behind it to allow this representation. Okay, so once you have that, you define all those arrows, all the relationships that I talked about before. I gave you some examples. You can actually go and say, okay, for the reasoner part of it, slide 30, I want you to use the OWL reasoner. So I'm going to use the information I have available on my OWL ontology, and I'm going to use that to fill in the values of my random variables. And so now I can go back to protege and give the values. Have member 1, 2, and 3, person 1. They have these certain relationships. This guy is a member of that committee, and so on. Once I do that, I can enter a query and say, okay, what is the probability that I have a suspicious procurement given this information that I have available? And then it's going to work as we did before, but now the information is going to be retrieved from my ontology. And I'm actually going to instantiate that and say, okay, given this specific information, this network answers your question, and the probability is 60% that you have a suspicious procurement. Okay, so we showed that this actually, we are able to do that, which we were not able to do before with Prowl 1. So now my second contribution is about the methodology. And this methodology, I call it uncertainty modeling process for semantic technologies. So just refresh our memories again, what's the problem? The problem is that you have this system, it's going to do automated reasoning using probabilistic ontologies, but how do you come up with your model? So it's really complex to create this model. It's really hard to do it, especially because it involves both logic and uncertainty. So again, how do I come up with this model? So the problem is that Prowl, we have a lot being said about what Prowl is, how to implement it, where it can be used, have emerging literature on ontology engineering, but little has been said on how to create these probabilistic ontology models. And this lack of methodology, again, it's not just associated with Prowl, to other languages. Oh, yeah.
So you're in 35?
35, yeah.
Okay, thanks.
So this lack is not only associated to Prowl, it's also associated to other languages like Onto-Bayes, Bayes-OWL, PRMs, Markov logic networks, and so on. So that's why I propose this methodology, and this methodology is actually based on unified process. So this is a figure that is actually well known in the literature for a unified process. I'm going to be based on that, and I'm going to explain later what I actually added, what was my contribution. Okay, but I just want to give you some ideas here before. So in slide 36. We're going to have, during our modeling construction, modeling design, we're going to have different phases. You're going to have the inception where you think about the requirements that you have on your model. So you're going to have a lot more requirements on the beginning than throughout the end of your modeling process. Then you're going to, but also going to have some analysis and design. We're going to define some initial rules that you want to represent, uncertainty rules. For instance, that is from 4 rule that I explained to you before. And maybe you even have some testing before you have any implementation. Because before I actually create this complex probabilistic ontology model, I might want to just test this rule that I defined on my analysis and design with a simple Bayesian network and see if the behavior is what I expected. Then I can say, okay, this is what I want. Then I can create the more complex probabilistic ontology. And then all these different iterations that we go through every single discipline is called an iteration. And I have to call him back. Pause. Sorry, lost connection with Dr. Fabio Cozman. At least we have some battery yet, so. Hello, are you there?
Oh, yeah.
Okay.
Just, back.
Okay, I'm back. So slide 36. So basically, in some phases, you're going to need some more iterations to finish that phase. And basically, what I want now is to focus in just one iteration, and that's where my contribution is. So if you think about just one single iteration, where we go through requirements, analysis, design, implementation, and test, well, what are the steps? What do you need to do to design a probabilistic ontology? So there are processes out there that define how to, there are unified processes that define how to model softwares. So you have a software engineering process. You have other types of processes. But now I'm defining a process to define probabilistic ontologies. So that's where my contribution is. And that's where I define all the different activities and things you need to do in each step. So for instance, the requirements you need to think of is, well, what do I need to achieve with this model? Okay, what is my ultimate goal? So, well, I want to find suspicious procurements. That's what I want to do. But how is your model going to know you have a suspicious procurement? So the model has to be able to answer some questions, which is going to indicate that it's more likely that you have a suspicious procurement. And you're going to have to ask questions like, is there any relationship between the committee of the procurement and the enterprises participating on that procurement? Well, how do you know that? How is the tool, how is the model going to be able to know to answer that query? Well, then you have to tell it that it needs some kind of evidence. So look if they are siblings, if these people live at the same address, if they have the same last name, and so on. Once you define those rules, then those requirements, then you can look at those requirements and see, what am I talking about? So what's the vocabulary that I'm using here? So you can start looking for those types and attributes and relationships they talk about in the ontology. So I'm going to have a person, I'm talking about procurement, so I'm going to have procurement. I'm going to talk about enterprise participating in a procurement, so participating is going to be a relationship, and so on. Once you have defined those entities, attributes, and relationships, you go define your rules. So, how should I use this evidence to answer this question? Well, if a member of a committee lives at the same address as a person responsible for that enterprise participating on that procurement, then it's more likely they are related. Then it's more likely that you have going to lower competition because you're going to tell your brother that, privileged information. So you're going to use these stochastic rules and you're going to define all these different things saying pretty much how you answer this question using this evidence. Then, in order to make your life easier because you're going to have a lot of rules and a lot of information, you're going to group them in a coherent way, and then you pretty much finish your analysis and design requirement stage. And you can see here that all these steps that I defined, they're language independent. It doesn't matter if I'm using Prowl, if I'm using PRM, or anything else. This applies to anything. But now you want to actually implement using some language, then it has to be specific to the language you're using. And I'm going to talk on how to do it in Prowl. So in Prowl, what you need to do is map these groupings here and these rules to M frags in our MEBN logic, right? So basically, this rule that I have here, if people live at the same address, then they're more likely to be related. That's what I'm putting in this M frag based on this rule. Once I have the structure of my MEBN model defined, then I can look at the rules again and say, okay, let's define the parameters. I can do that using an expert, which is going to give us some probability that might not be that accurate or that correct in the sense of a frequentist way of doing it. But we can also use learning to learn those parameters. Okay? So either way, once you do that, then we need to do some evaluation. And this evaluation is going to see, okay, did I cover all the requirements that I said that my model needed to have? Did I do everything that I needed? And now, let's create some different use cases, some different scenarios, and verify if the model is behaving as expected. So we try some thresholds and see, okay, is this what I expected? Is this what the expert expected? So I'm going to talk about a little bit more in detail of this test phase, this evaluation. So when I'm evaluating this procurement fraud example, I'm going to focus here on the case-based evaluation, and it's slide 38. And I actually created 3 different scenarios. For this case, I was the expert because I work for the this Brazilian office that does auditing inspection, so I know about this stuff. Not a lot, but at least enough to be able to understand this stuff. And basically, the hypothesis that I have on all these 3 different scenarios is suspicious if the procurement is suspicious and if the committee on that procurement is suspicious. Okay? And then what I do is I have all these different kinds of evidence, and you can see more detail on my dissertation. But basically, on the 3 scenarios, one has evidence that does not support the hypothesis. One has conflict information because some of the evidence support the hypothesis, some does not. And then finally, the last one, you have a lot of evidence that support the hypothesis of having of this hypothesis here. Okay, and then I have to define, when I'm defining this test, I have to define the expected result before I actually run my model, right? So the expected result here on the top is that, when I don't have evidence supporting anything suspicious, I expect to get a low probability of the hypothesis given the evidence. On the other case, where I have conflict information, well, I'm really not sure, but it's going to be somewhere between 10 and 50%. And those are just numbers I came up with. It could be 55, 60. The idea is I can't really tell. It's not low, it's not high. It's somewhere in the middle. And also, when I have hypothesis evidence supporting the hypothesis, now I expect for hypothesis A to be a probability greater than 50%, because that's the evidence I added to support hypothesis A, and I did not change for hypothesis B from the second scenario. So that's why I still expect for the committee, suspicious committee, to be between 10 and 50%. And then you can see when I actually ran these models, I got the result I was expecting. So it's 2% on the first case where I was expecting a low probability, 20 and 30%, 29% for the cases where I'm not sure. And for the cases that I thought it should be suspicious, I got a probability greater than 50%. And just to explain here, these probabilities are not, I inflated myself, these probabilities. So you would not expect the probability of having fraud to be 2%. That's high if you think about the number of procurements you have and the number of frauds you have in each procurement. The idea here is I inflated to make it easier for experts back in Brazil to understand what I'm talking about, low probability. They understand that 2 is low given 100%. They understand that 10, 2 is low, and greater than 50 is high, and those kind of, or it's suspicious at least, those kind of things. But we could easily go back and change the probabilities to be 0.001 and 0.01. So if you grow 10, 100 times, then that's something that indicates that you also have likelihood that this is suspicious. But then I would not be talking about greater than 50%. I would say, did it increase in the order of 10 magnitude or something like that? Okay, so I'm not going to explain a lot of detail here, but I just want to say that I did the same thing for maritime domain awareness. So a different use case with different requirements, with different rules, different entities and relationships, but the way I created the model was the same. I went through the same steps which I proposed in my dissertation. I created this MEBN model, I created this probabilistic ontology, and then I did some evaluation. And let's talk a little bit about the evaluation for this model. What we did here, we actually separated in 2 different tests. One was manual and one was automatic. So for the manual case, created 4 different major categories where I had a possible bomb plan with a fishing ship and a merchant ship, and a possible exchange of illicit cargo using a fishing ship and using a merchant ship. And then I created 5 variations like I did with the scenario 1, 2, 3 from the previous one. I did here, let's look at evidence that says that it's sure positive. It's like 40. That looks positive, unsure because conflict information, looks negative, and sure negative. And so that was a total of 20 different use cases, 20 different scenarios. And I, together with the subject matter experts, one of them is here. We look at this stuff and does it make sense? Oh yeah, it makes sense because the probability seems to be, what we're talking about here. It's sure positive, it's sure negative, and so on. And the other thing we did is actually we did some automatic case-based evaluation, where we used a simulation tool that we developed in a Prognos project developed for the U.S. Navy, ONR, and to generate some ground truth. So we have the simulation where you have different ships and things are happening, and you have some terrorist ships, slide 41, and you have all this different information. So you actually know when a ship is a terrorist, it's a ship of interest. But it just, because you simulated that, okay? But then you just generate reports based on that simulation. So you say, the probability of getting this kind of reports is like 70%, it's usually right, and so on. So we do that, generate some reports, then we use those reports to infer the results and compare to the ground truth. And that generated this confusion matrix I showed down here with a threshold of 50%. So basically what we have is, is this ship a ship of interest? Is there a terrorist? Is there a terrorist inside or something? So you can see here the real classification is true and false. For true, of course, we have much less. I have 27 cases, but when the ship is normal, we have 588 cases. And you can see here that the probability was greater than 50% in 24 of the cases that it was actually a terrorist. So in three out of 27, we got the wrong result, which said the probability was lower than 50% when it actually should be greater. And the other way around, we said we just in 11 cases out of 588 cases, we said that it was actually a terrorist when it was not. So we said the probability was greater than 50 when it should be lower than 50. And you can see here the probability is on the side. So a true positive 89% of the cases, and a true negative 98% of the cases. So those are good results for the scenario created. Finding some conclusions. I talked about the problem of mapping, showed the solution in Prowl 2, how I do that mapping. There are some more things in the dissertation you can look at there. Also talked about how to reuse existing types in null, led the development of a tool that allows you to use this new language, and also develop a new methodology that guides you step by step on how to create this probabilistic ontology. And created 2 use cases showing that you can actually apply this methodology to create your models. So future work, there are quite a few we can think of. Of course, the implementation that I showed you is just a proof of concept tool. We have actually a master's students working in Brazil on a more mature implementation of Prowl 2. It's going to incorporate more features of it. We also have another student working on implementing a tool that's going to help you create your model. So it's going to guide you. Okay, in the requirements, you should be looking into doing this, and then it's going to allow you to put that information into software and so on. But for Prowl to actually be widely used in the community, we have to solve some of the problems we have. And they're also associated to actually MEBN, which is MEBN reasoning and MEBN learning. The current algorithm we have implemented for MEBN is an exact algorithm. And it can take a lot of time to compute these things. So we need to have some kind of approximate reasoning or some lifted inference reasoning, which is a way of not repeating computation, so saving time and memory and things like that. And also, it would be interesting to look at sub-languages of Prowl 2 and analyze the complexity of each. So, for instance, I talk about you're allowed in Prowl 2 to represent n-array random variables. Well, what if you restrict yourself to just 2-place random variables? How much do you gain as far as complexity goes, in the sense that how much faster does your algorithm get? What if you constrain your context nodes to just description logic and not full first order logic? So those things it would be interesting to analyze and see what we get. Also, it would be interesting to have some learning algorithm for MEBN models, which we don't have any algorithm for learning yet for these more complex models. We do have for Bayesian networks, and we could apply some of those stuff to do some parameter learning for MEBN, but structural learning would be harder. Have a question?
Yeah, I'm just curious, can you do what-ifs with the model? Like work backwards, say, I want to establish certain probability for the hypothesis, and what do I need, what kind of evidence do I need to working backwards to get that?
No, I mean, there is nothing implemented in that sense. You could do simulation like you do in Bayesian network. You could do sampling. You could say that these nodes have these values, and then you can sample everything else. But we don't have anything implemented for MEBN. And I think that would be actually useful to understand, what kind of evidence pops up when you're looking at terrorists and things like that.
There are published algorithms, which we don't have implemented in this tool, for saying, okay, I've set this evidence, and I've set that evidence, and I've set that evidence. Now explain the evidence for me. Find the most likely hypotheses that would explain this evidence. So there are algorithms for doing that.
Okay.
That we have not done anything specific for this tool.
And
for
especially
MEBN.
as these models get more complicated, understanding why they do what they do is really a challenge.
Yeah.
Explanation.
Yeah. And another thing is have some random variables be solved in an external tool. So call an external tool that defines deterministically if a number is less than another number. That's really easy in any programming language, but if you live just to logic, that can get really complicated, especially if you're looking at equations, math. A linear equation can be solved really easily and fast on an external tool, but if you leave it to the logic, it can get really ugly. So it would be interesting to allow these probabilistic ontologies to call external tools to solve specific tasks and give you the value of that random variable when it's deterministic at least. And finally, the last thing I want to talk about is, it would be interesting to get that process that I defined, the methodology, and put into this Eclipse process framework where you can actually reuse other processes like open unified process, and you can tailor it to create your own. And then once you do that, you create different roles and create different activities and disciplines, and you can then publish on the web, and people can have access to all that documentation examples, and they can actually contribute to it. So that's something would be really interesting to see someone do it. And maybe someone here would be interested in. And also, again, just publications, I basically had 9 papers published in workshops and conferences, 6 book chapters, 3 journal papers. 1 is accepted in conditions. I'm really not sure what happened there, but still waiting on the final result. But 2 of them I'm actually working on right now, so I haven't submitted yet. And 2 added work. And I did participate in some international workshops on this area of probabilistic ontology. Well, thank you very much.
Presenting a paper next week.
That's true, yeah. On this stuff, on the methodology.